All right, our next topics in the study of Calculus 1, we see in section 2 here in chapter 3, which covers the product and quotient rules. And as I mentioned at the end of our last section, the product and quotient rules are going to allow us to work with taking the derivative of some slightly more complex expressions. And let's see what we have available to look at here. First, the product rule. And again, these slides contain a lot of backstory and sort of building examples that lead us up to the actual rules, like the product rule. And so I'll be pausing as I go through these slides so that you can check out some of the text and illustrations that are written here. All of these things that you're seeing on these slides are true and they're good, and my focus is going to be getting you to the rule and teaching you how to use the rule without exposing you to, or at least marching you step by step through the entirety of the backstory of the product rule and quotient rule in this case. So number 2 that you're seeing on this screen is the first really somewhat clear articulation of what the product rule allows us to do. And this is the most formal articulation here. And what this says in this box is that if we're taking the derivative of a product of two functions, they don't have to be polynomial functions. They can have square roots or fractions, or they could be exponential functions, one of them or both of them. But if we're taking the derivative of that product, the result is the same as if we left the first of those functions alone, but multiplied it by the derivative of the second function, and then we add and then switch. Keep the second function the same, but multiply it by the derivative of the first function. There are many different ways of representing what is written in this box here, telling us what the product rule is. Another way that maybe you want to think of this that makes it look considerably less overwhelming would be to say, let's put f and g plus f and g, and then in this first term right here, I'm going to take the derivative of g. And in the second term here, I'm going to take the derivative of f. The order is a little bit different from what is typed up into these notes. However, you see that f and g are present in both of those terms. And in one term, we're taking the derivative of g, and in the other term, we're taking the derivative of f. Because this is addition, it doesn't even matter if you were to sort of flip-flop these two terms. You could accidentally write them out of order. There isn't really an out of order. Because of the commutative property of addition, you can write these in whichever order you want, as long as in each term you're taking the derivative of one and then the other of the two factors or two functions. So let's see some typed examples of the product rule. In part A, our function is equal to x times e to the x. And here's our solution process. F prime is equal to the derivative of x e to the x. And in our second line here, our first function remains the same, times the derivative of the second function, plus the second function times the derivative of the first function. We haven't even taken any derivatives yet. We're just laying out what it is that we're going to do in greater detail. And then we go ahead with the actual process. The derivative of e to the x is e to the x. So there it is. The first function was just x. That didn't change, so that's still there. Our plus sign is here. And then there's the second function, e to the x. That has not been touched. However, we're going to multiply it by the derivative of the first function, and the derivative of x is 1. And the derivative of e to the x is e to the x. We know that from our previous section. Then all you have to do once you've got this statement and you have taken your couple of derivatives is to clean it up or simplify sometimes. In this case, we have two terms. There's this term and this term. This term and this term. This times 1 doesn't do anything, so forget about that. These two terms each contain a multiple or a factor of e to the x. So in these notes, that factor of e to the x has been factored out. Normally, I would be willing to guess, or willing to bet, that normally when you factor out a common factor, you would write it first. And if you distribute multiplication by e to the x to both of these terms, you will come back here and get these two terms. 3 times 2, 2 times 3, they both equal 6. That's the commutative property of multiplication. The fact that I wrote the factored expression like this, and that the author has written the factored expression like this with the multiple of e to the x at the end, that's okay. It's equivalent. It's still the product of two things. We're just changing the order in which those two factors are written. I personally wouldn't be surprised if you found multiple choice options where you didn't have to factor the e to the x out at all. Or if you're typing this in as a free response answer into online software, I wouldn't be surprised if you were not required to factor out the e to the x. You can read through this. Here what you're seeing is the second derivative. So we're taking the derivative of the answer that we just found. And you can go through and see how the product rule is being used in order to find this, which is the second derivative. And the third derivative and the fourth derivative, interesting, it seems that the only thing that keeps changing is this additional constant value in here. And you could go back through and try to discern why it is that that's the only result as we're going from one derivative to the next. And then here's a generalized statement about the nth derivative of that particular expression. This is not being highlighted because it is a function that you're going to be seeing all the time. It's not going to be showing up. Little variations of it aren't going to be showing up in half of the problems that you're going to be working on. But it is an interesting phenomenon that n value, as it increases as you take subsequent derivatives, that n value keeps increasing. And then there's the quotient rule. The result of multiplication is a product. The result of division is called the quotient. That's why this is called the quotient rule, because it involves division. And here we're seeing capital delta, which involves change. And you are more than welcome to read this. Some of you, it would do you some good to give you an added depth of understanding. My guess is that a lot of you would find this to be overwhelming and distracting and not all that helpful. However, it is here for your review. And in this box, we're seeing the quotient rule. This is, again, maybe not the clearest, or at least the most compact or concise description of the quotient rule, but it is true. It's correct. In the numerator over here, we're seeing f of x. In the denominator, there's g of x. And we're going to be taking the derivative of that fraction or that quotient. And then in the numerator, on the other side of our equal sign, we see the denominator times the derivative of the numerator minus this time, and then they switch. It's the numerator that's untouched times the derivative of the denominator. And in the denominator of the entire right-hand side of our equation, we're seeing the original denominator being squared. If you were to articulate that, there's the derivative of the quotient, is the denominator times the derivative of the numerator minus the you can read. I'm pretty sure I just said almost exactly those words. This is difficult for me to remember. Memorization is not my strong suit. I've already got a lot on my mind that I have to know. As a college student, maybe I've got 4 or 5 different courses. If I could keep the memorization at a minimum, I'd love to, but if there's kind of a nice mnemonic device that I can use to memorize some stuff, that's helpful. And the thing that was most helpful to me when someone was describing how to memorize the quotient rule, they said, don't think of it as taking the derivative of f of x over g of x. Have a look at this. They said, think of it as taking the derivative of the top over the bottom, which is the high over the low. And if that's the case, then we can reframe the right-hand side as low times the derivative of high minus high times the derivative of low, all over low times low. And if you say that even faster, it becomes low d high minus high d low, all over low low, which is a little bit more fun to say than this, and I think it's a little bit more memorable also. So if that works for you, use that. If you've heard of a different mnemonic and you'd like to share that with me, that would be great. You could leave it in the comments. As always, choose whatever is going to work for you and make the best, give you the most accurate results consistently. And then let's check out an example. So here we've got y equals a fraction. We can see our 2 functions, numerator and denominator. And here is low times the derivative of high minus high times the derivative of low, all over low low, or low squared. After that, we have to take a couple derivatives. Our first derivative comes down here. The derivative of this expression we're finding here. You should know by now how to take derivatives of those types of polynomials. And from there, it's algebra. We are foiling here. We're distributing in from the left here. You have to multiply that 3x squared in times all 3 terms in parentheses. That takes us down to our next version of the right-hand side of our equation. Here, the only thing we have to do is distribute this minus sign out. And once you've distributed and changed all of your signs there, you will need to combine like terms. So this was FOIL and distribute. Here we had to distribute from the right, and we combined like terms, and that's how we arrived at this last expression down here. We've got our 4th power, 3rd power, 2nd power, 1st power, constant value, all over the denominator squared. And that's it. If it were possible to factor the numerator and cancel it out with a factor of x to the 3rd plus 6 from the denominator, we would. It's very infrequent that that happens, but you're welcome to glance at it and see if that's a possibility. Otherwise, you're putting a box around that as your final answer. I saw this and thought it was a nice little recap of the different derivatives that we've taken so far. The derivative of a constant value is equal to 0. The derivative of a power function, we take our exponent and multiply it out front, and then decrease that exponent by 1. We see that the derivative of e to the x is e to the x. And once we bring in the chain rule, that's going to get a little bit more involved, but for starters, that's pretty good. What this tells us is that we can factor a constant out of the derivative process. I think we previously saw this as the derivative with respect to x of c times f of x is equal to c times the derivative with respect to x of f of x. So you can factor a constant out of the derivative process is the moral of the story there. The derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. Here's our product rule, and here's our quotient rule. Amazing that that's everything that we've covered just in 2 sections, and we were able to say it in a couple of breaths. So that's the end of this section. Let's pop over and take a look at the homework assignment that corresponds to 3.2. Problem number 1 is requires the use of the product rule. Here you're being asked to use the product rule to take the derivative. If I can get my pen to work, there we go. And here the suggestion is being made that you FOIL this out, combine like terms, and then take the derivative as you would have in section 1. And you could compare and see if you get the same answers. It's not the worst idea in the world. It's nice to know that you could FOIL, combine like terms, and then take the derivative in order to check your work. But try to do this using the product rule. See what you get. Here you are being asked to differentiate or take the derivative. Let me remind you that the derivative of this statement is equal to 5 times the derivative of this statement. So if you use the product rule to take the derivative of this, you're going to get 5 times some stuff plus some stuff, and then you'll have to distribute that 5 in after you've applied the product rule. So I would highly recommend factoring the 5 out of the derivative process in that problem and then multiply it back in at the end. Problem number 3 is a quotient rule problem. I leave you to try that on your own. I put a star next to problem number 4 because technically this problem should require the use of the chain rule. The derivative of this, let's have a look at it. Y prime is equal to low, which is t minus 2 squared, times the derivative of the numerator, d high, derivative of t is just 1, minus high, which is the numerator, t, times d low. Now the derivative of the denominator, I'm going to take this exponent of 2, and I'm going to multiply it out front like it's a coefficient, so there's the multiple of 2. Then this isn't just a variable, it's an expression, which is why the chain rule should be used here. Don't worry about that, we'll get to it. So keep the t minus 2 in there. Decrease this exponent by 1, so it was squared, now it's to the first power. We don't normally write the first power. If you want to write that in your notes, if it's beneficial so you can see that the exponent has been decreased, that's fine. I'm going to erase it though. And then technically by the chain rule, what we should be doing right here is multiplying by the derivative of t minus 2. The derivative of t minus 2, however, is just 1. So don't worry about including anything there at the moment. When we get to section 4 and we talk about the chain rule, we'll get into it. But at the moment, don't worry. It's not going to impact your final answer for this particular problem. Just realize in a couple of sections I'm going to add something on to that process where we have to multiply by the derivative of what was in these parentheses. And I'll call it the chain rule. And then we keep our denominator low. We have to do our denominator squared. And that's t minus 2 squared squared. So that's going to end up going to the 4th power. FOIL this, take the negative t or the negative 2t and distribute it into these parentheses, combine like terms, and your numerator will be all set, and I would leave this denominator as t minus 2 to the 4th power. All right, that should get you started on question number 4. I just wanted to really, my primary concern was addressing this denominator that had a parentheses being raised to a power. Number 5, quotient rule. Pretty typical. Remember that this is the same thing as t to the 1/2 power. Number 6, you're being asked for the first and second derivative. Don't forget that the derivative of e to the x is e to the x, and the derivative of x to the 9/2 power is 9/2 x to the 7/2. Take that exponent, multiply it out front like it's a coefficient, decrease the exponent by 1. So 9/2 would become 7/2 in this case. Once you get a final answer for this, you're going to have to take the derivative again, which is going to involve the product rule again. So be patient and keep applying the product rule as necessary. Find an equation of the tangent line. So here you're going to use the quotient rule to take the derivative. And remember that in order to design the equation of a line, you need y minus y1 equals m times x minus x1. Here is x1, y1, which is nice because that means all you need is the slope. How am I going to figure out the slope? You're going to take the derivative of the given equation. In this case, that'll be y prime. And you're going to plug in an x value. In this case, an x value of 1, because we're concerned about the slope of the tangent line at the point where x equals 1. So figure out y prime, then plug in a 1. Let me say that again. Once you find the derivative of this, call it y prime. Once you have the derivative in terms of x, then plug in an x value of 1. Then you'll have y prime of 1 instead of y prime of x. That will equal your slope. Once you have x1, y1, and your m value, your slope, plugged into point slope form, which is what this is, you'll then have to convert that equation into y equals mx plus b, which is slope intercept form. That answer would go in this box. This says y equals because it's in slope intercept form for the equation of a line. Number 8 is cute, as we say in mathematics. You do need to find the derivative of f of x using the product rule. So step number 1 is to find f prime of x. You'll use the product rule. So you're going to get, we'll keep the e to the x times the derivative of g plus, now we'll take the derivative of e to the x, which is e to the x, and we'll leave g as it was, just g of x. Now, in order to find f prime of 0, you're going to have to plug a 0 in here, 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 and here. You need to know what e to the power of 0 is. Anything to the power of 0 is equal to 1. Wouldn't it be nice if somewhere they had told us what g prime of 0 is? And wouldn't it be nice if they had also told us what g of 0 is? So we're just plugging in some different values, do a last little bit of arithmetic, and you'll have your final answer. Number 9 is clever. It's a little overwhelming. So let's look at it quickly. If I can get the whole thing on the screen. There we go. So we're estimating the rate at which total personal income is rising in a metropolitan area. What they don't explicitly say is how to calculate total personal income. And you need to be aware that total personal income is equal to What variables was I going to use? Population times average annual income per capita. And per capita means per person. So this is total personal income for the entire metropolitan area is equal to the average annual income per person times the total number of people. I think that sounds pretty reasonable. And then let's look at the question again from the very beginning. In this exercise, we estimate the rate at which, I see the word rate, I'm thinking derivative. Rate of change, instantaneous rate of change. We estimate the rate at which total personal income is rising. So we're assuming it's going to be a positive number. So I need to take the derivative of total personal income because it's on the rise, and I want to know the rate at which it's rising, which reminds me, let's skip down to the question. Use the product rule and these figures to estimate the rate at which total personal income was rising in the area in 1999, rounding to 3 decimal places. We're going to answer in billions per year, which doesn't make sense. It's the total, or it's no surprise that it's in billions per year. It's the total personal income for an entire metropolitan area. Let's take the derivative of TPI. We're going to need to keep the population value and then multiply by the derivative of average annual income per capita, plus, and then we'll take the derivative of population and we'll multiply that by average annual income. I'm just making things up now. Average annual income per capita. Now I've put, look at this. I put derivative of average annual income per capita and derivative of population. We were not given an equation describing average annual income per capita, nor were we given an equation describing population. So how am I supposed to take the derivative of those things? I'm not. Remember that derivative is synonymous with rate of change. Let's start reading the problem. In 1999, the population in this area was whatever it says there, 978,300. That is our population. The population was increasing. That's a rate of change. Rate of change is synonymous with derivative. The population was increasing at roughly 100,000. So let's start filling these in. Population was 978,300 plus the rate of change of population was 10,000. The average annual income was 33,162. Average annual income per capita, okay, 33,162. And this average was increasing. This average, the average annual income per capita, this average was increasing, rate of change, derivative, at about $1,300 per year. Now it's multiplication and addition. But what I want you to make sure that you take a moment to connect with, even if you watch my articulation of this problem from the beginning, make sure that you're connecting the English words that are used here, not the mathematical words, but the English words, and connecting them to what they mean mathematically, conceptually, and symbolically. So, like I wrote derivative right here, but we never actually took the derivative of anything. We needed to interpret derivative as rate of change, or just rate. And rate can either be increasing or decreasing, or I suppose it could be 0. But in this case, we saw the word increasing twice in this problem, right in the middle, right up there. Yep, there it is. Increasing, increasing. Those words need to indicate to you that we're talking about a derivative, a rate of change, and since it's increasing, it happens to be positive. Okay? Combining that and connecting it with the product rule in this very kind of rough way that I sketched out the derivative of the relationship between population and average annual income per capita, and realizing that I had to create this original equation in order to use the product rule and take the derivative of it in a very symbolic way before I started plugging in numbers. So read through the original problem again and see if you can find the indicators for you that would compel you to create the initial equation that I've circled here. Without that, you can't take the derivative of it using the product rule. And without having taken the derivative using the product rule to get to here, you don't have the blanks to fill in with the given information. So you need to be capable of that. There's one more example or word problem that comes after that. I think you can handle that one, so I'm going to let you wrestle with that one. I thank you for hanging with me for this talk about the product rule and the quotient rule. And I believe in our next section, we're going to look at some trig functions. So that'll be a little change of pace. That'll be section 3. I will see you there. Thanks.